Hello. Good. Yeah. Okay. Here's how it works. Hello, everyone. Thanks for coming to the recitation. Just get started. And maybe some of you are drawing from my email. So you probably know what we're going to talk about. We're going to talk about subgradient, dual norm, and yeah, here's this little cute thing. Dual norm, and finally steepest descent. Okay, so first let's do a brief review of subgradient. This week we've been talking about subgradient. It's super useful for a lot of things, mostly for proximal descent, because it's the first thing we'll use it on. And for the intuition behind subgradient is, of course, the gradient. And the gradient, the intuition actually comes from the fact that every convex function has a tangent plane that actually lower bounds the function. So if we start from the very beginning, we have a convex function f of x, right? And at every point, there is a plane that lower bounds this function, right? And this plane could be the tangent plane. So basically, what it says is the gradient of this plane, which is like this delta y over delta x, could be the over delta x could be the differential of f at this particular point. So this tangent plane can lower bound this function. That's where we start from. That's where the whole class starts from. This is the intuitive definition of convex functions. Okay. And now, not every convex function is differentiable. So what can we say about this tangent plane that lower bounds this function when this function is not differentiable? And here it comes the definition of subgradient. So if I have a function, for example, this is my f of x in one dimensional, and it's not differentiable at this particular point. But I still can find like tangent planes that lower bounds this function, because this function is still convex. And I can not only find one tangent plane, I can actually find a lot of planes that lower bounds this function. And all the gradient of these planes, these lower bounding planes, form the subgradient. So how do I characterize that this plane lower bounds this function? Basically, I say that, for example, the gradient of, for example, this plane is given by G transpose X plus some number, I don't know, some T. Right? This is how we describe a plane. This is the gradient, and this is some constant. And to say that fx is upper bounded by this plane, is lower bounded by this plane, basically we say fy is greater or equal to fx plus G transpose y minus x for any y. Right? So far everything is very simple, taught in class. Just a recap. Okay, so let's see some examples. In class, we've seen many examples, but I just want to briefly recite the most important ones. There's one example. Oh, by the way, if I complete the definition, I should write the subgradient is actually a set of all the tangents, of all the gradients of these planes. Okay, so there are several examples. I want to talk about 3 actually. One example is okay, the one norm. Similarly, I have the infinity norm, and also similar to the one norm, but actually this is an indicator function that this one norm is smaller than 1. Okay, and here in convex optimization, when you talk about IC of x, when x is in C, of course, it's 0. No, this is not the convention in other courses, but for convex optimization, when x is in C, this function takes value 0, and when x is not in C, this takes function plus infinity. Have I turned the slide on? Or do you have trouble seeing the board? No. Okay. Oh, cool. Thank you. Thank you. Right. So for the first function, if I draw the level, what's called the level map of the first function on 2-dimensional. So the first function when x belongs to 2D, okay? And I know if this is the level map for f equals to 1, for example, right? You call this shape. Because the definition of one norm is the sum of the coordinates, and everything on this segment has the sum 1. And this, for example, is the value, the level map of f equals to 2. So so now, what are the subgradients of this function? The subgradients exist everywhere because this is a and this is a convex function. So of course here I have to come to my little thing, a little tool. Okay, so you can see this is aligned this way, this way. Okay, so this is x-axis, this is y-axis. So if I'm here, somewhere here, so how many planes are there to support to lower bound my little pyramid, inverted pyramid? 1, right? So the subgradient here should go this way. And the scale is also 1 because there's only one plane. If I go this, if I extend my xy coordinate by a unit length, then my movement to upwards on this plane is fixed, right? So if this is the supporting, if this is the plane that lower bounds the function value at this point, then my gradient cannot be larger or smaller. Because if the gradient is larger, then I actually cut through the pyramid. Okay.
The subgradient is not the function. It's not the function. But here is not a function. It's not the function.
The subgradient is this vector. It's a.
Yeah, but when the function is differentiable, it is the function, right?
Yeah.
It's not the function. It's the one normal.
No. So the tangent hyperplane
will
be given by its normal vector. Right? How do you represent a tangent hyperplane by its normal vector?
I see.
Oh, it is the so here's the question. Yeah, that's a good question. That's a confusion I also had. This is the level map. This is the map for f equals to 1. Okay, but if you imagine this, the tangent is this direction. The tangent is actually not on this space. The tangent plane is something different from this plane. But when you say this is normal, it is because you are constraining f to be 1. It's normal to f equals to 1, but tangent to the function f. Okay, so if we go here, this same plane will also lower bound the function at this value, right? So I have the same tangent, the same subgradient like this. Basically a translation of this subgradient. I can also have a subgradient which is a translation from here. And if you have a plane that supports, that underbounds this shape from here, you can actually get something in between, some directions, some subgradient directions between these two. And the scale value of this subgradient is also just one scale. You cannot extend it or contract it because basically at any direction, there's only one plane that lower bounds the inverted pyramid. So if you listen carefully and have a good memory, this scale should be a convex combination of the two. So if I draw a dotted line here, the scale should match here. Convex combination of these two vectors is anything that's that will end on this line segment, not exceeding these 2 points. So as a result, you see this plot in the book, in the course lecture, which basically draws the shaded area like this. But actually, it's the vector that actually lands on this line segment. So this is our first example. The second example is the infinity norm. And the infinity norm, the level map of the infinity norm is something like this. In 2D, it's not not always a rotation of the one norm. In 2D it is, but in general it's not always. But I don't want to go to details. It's similar case to that one geometrically. Okay, and what I want to make you to be careful about is the third thing, which now I'm not drawing the level map. Well, I could be drawing the level map, but this is the set that inside the set everything is 0. The function is 0. Outside this set, this function is plus infinity. So here, there's a huge jump that actually from 0 to infinity. So any scale at the correct direction can lower bound this function value. So basically, I can be unit length, the subgradient. I could be twice that length. I could be like triple that length. Any length works here. That's why this is called the normal cone. Cone means it works if you extend the length. So you see the difference. This length is fixed. This is not allowed. But here, the length is arbitrary, and it's a cone. For every point on this boundary, there is a cone. And this cone is called normal cone. Okay, and here, anything that lies in this area, in this direction, between these two lines, like anything here works as a subgradient. Okay. So is this going too slow or too fast?
Also, on that here, you mean that when the level is at like infinity level, right?
Oh, level map. So if at any real number, f equals to anything t, where t is not smaller than infinity, greater than 0. Any positive real level map is this shape.
Yeah, but I mean, this one is for the number 3, so it's infinity indicator function.
Yeah, yeah, indicator function. Okay, so this is subgradient. Some things that are very important examples for subgradients are, well, some facts about subgradients are these. So if I write this should be arc mean of x, y minus x 2 norm squared plus lambda times x1. The optimal value for this optimization problem is known. Okay? And this is a very important fact. That's the basis for proximal descent, for proximal gradient descent. So the optimal value for this part is the soft thresholding for y. This is known exactly. And what is this useful? It's because in proximal gradient descent, basically there are 2 steps. One step is you only consider the continuous part of the objective function, and you make a descent. You make a gradient descent. You only consider the continuous part, and then you have you make a quadratic like 2 norm approximation, quadratic approximation near that point that you just jumped to, which is this part. And you apply your non-continuous part. And usually, for example, the non-continuous part is the L1 penalty. Then you know the result exactly. So this is a known result, and it is important in solving like L1 penalized objectives. Okay. And I can make a slight extension. If I have a matrix value, this is something that Ryan will talk about soon, but it doesn't hurt if you see it again. But for a matrix, basically, what replaces the 2 norm here is Frobenius norm, and here I have a here I should have a trace norm, or what is called the nuclear norm, to replace 1 norm. And here, instead of this soft thresholding, I have a soft thresholding on the singular values to replace soft thresholding on entry values. And this is also known result. Oh, if you want to prove this, basically you take the gradient and you verify that here the subgradient contains 0 for this value. A question?
Is there a vector path on the...
Oh, yeah, great point. There it is. Okay. And something also known, something also known in the class is this. I should write Z here. This is a result from by applying a property of subgradient, you can reach this result. And this is more interesting. This relates to everything I'll talk about later, so I'll come to this immediately. But before that, let me just recap the important properties about subgradient. So I should write on this part, I guess. So important properties Of course, here you have your linear combination of function values. Subgradient of a linear combination is a linear combination of the subgradients. It's just like a gradient, just like a function differential. Similar, very similar. And you also have the chain rule. A transpose subgradient of f at this value, ax plus b. If you want to understand this, you need to know that this subgradient is in terms of f, and this subgradient is in terms of f. Sorry, I meant towards x. So you want to go all the way through in, but here you only stay at the surface level, and you take that value. So it's also very similar to differential chain rule. There's nothing special here. What makes subgradient what's a very important property is this. If I have a function that is the maximum of a finite number of functions, that gives me that the subgradient is a, so does anyone remember what's here? Sorry? Yeah, convex hull of all these subgradients of every function. And here, it only applies to these functions that actually reach the maximum value. So it only applies to here. Right? Only applies to the indices of which the functions reach the maximum level value. And it's also true under mild conditions by replacing this I to a real indicator. So it's not limited to be finite or countable. It could be anything, real number. And here you also have this, but you also have this part S. The indices that reaches the maximum value, but before the convex operator, you have a closure operator on top. So that's because your set doesn't necessarily be closed. So it's just to be safe. Okay. And so we can see some examples, I guess. Yeah. So in the good old days, there used to be a homework problem. And this homework problem is to solve the subdifferential of the L1 norm using this property. Has Ryan talked about this in class? No? But it's pretty straightforward, right? Because your function value, L1 norm, is a summation of the absolute value of every indices. So it's just this condition. And so you can basically apply it. You just get the conclusion that it becomes the convex hull of all union of subdifferential of this particular value when this entry reaches the maximum. So that is here xi equals L1 norm. Yes. Oh, that's a nice catch. Yeah. Yeah. Max. Yeah. This is very nice. Yeah. And here, okay. Yeah, that's a nice catch. Here, the subgradient is towards the vector x. So if I define S of Si to be the subgradient of xi towards this index, this entry, then basically this part becomes Si times Ei. And entry-wise, the subgradient of absolute value is the sign of xi when xi is not 0, and the interval -1, 1 when xi is 0. Did I mistake anything? Okay, so if we visualize what we are getting, this is our infinity norm. And right, this is my x1, this is my x2. If I have x that rests here, then the index that reaches the maximum value is the first index. So that means my subgradient only works towards the first index, first direction. In here, I can work towards anything in the convex combination of these two vectors, anything here. But it has to reach this line segment. And at point 0, both my coordinates reaches its maximum, and their negatives also reach their maximum. So my gradient actually rests on this diamond. Okay. Yeah, you guys know a lot. But nowadays we don't have these simple questions to ask, and I couldn't even get this one right. Nowadays we have more complex things. So we were told that, for example, if I still take this example of x infinity norm, we were told right there, I'll just copy that. Z1 norm smaller or equal to 1. So as an outline, I was jumping from subgradient to what I want to talk about as a second topic, which is dual norms. Okay. This is subgradient. I missed one term. Right. So Ryan just put this in his slides. He didn't justify for this one. I wouldn't either, but I would give you some intuitions so that you feel this to be comfortable. So if we go back to the very beginning, the intuition of the subgradient, what we are seeing is this. Suppose in one-dimensional, we have a function, okay? And for every point x, we have a tangent plane, or just a plane that lower bounds this function value, right? For every x, we get a g. That is the gradient of the tangent plane. And if it's non-differentiable, then this is the subgradient. But the point is, for every x, there's only one g. No, sorry, I say that again. The point is, the g is never repeating itself. That is because it's convex. It's convex. Everything is going upwards. Your gradient will not happen again. This slope only appears to this point. Later, you will have a larger slope. Earlier, you have a shallower slope. That's also true for subgradient, as long as it is convex. So if you plot x and you plot the gradient, the gradient at one index, because gradient can be in higher dimensions. Gradient can be have multiple multiple indices, multiple coordinates. If you just plot the first coordinates, you plot x, maybe x is a plane or something, but the gradient is always increasing. In case of a subgradient, it will have a jump, but then it will still be higher. It's always increasing.
Need not be strictly.
Sorry?
Need not be strictly increasing.
Not strictly.
For example, if your function is a hyperplane, if the function is piecewise linear.
Oh yeah.
So if it's strictly convex.
Yeah, that's true. Yeah, that's a good point. But anyways, it is increasing, not decreasing. And the good things won't happen again. So that suggests us, if I have a gradient or a subgradient, can I find almost uniquely this x that is registered with this gradient? This x could be a point or it could be a line segment on this x coordinate. So to find g, we use the definition like that, right? The very beginning. That's how we define g. And how we define x from g, there's a very smart way. So how do we find this x if we have the gradient? The way to find x, so suppose you have this plane, okay? So every gradient corresponds to a set of planes. So it could be this plane or a set of parallel planes. So you could you could push this plane from the far end towards the function until it meets the function. When it meets the function here, you have this point. This is the point that's registered with this tangent plane. Everyone following? Okay, great. So mathematically, this x, which I'll denote as x star, is our max of x, g transpose x minus fx. I'll explain this on the graph. So g transpose x is the tangent, is the plane with the same gradient at the origin, right? When x equals to 0, this function becomes 0. So it's the plane with the same gradient but at the origin. And this is the first term. Okay, and the second term is the function value. So what this is doing is it's finding the x such that this difference becomes the largest. And when the difference become the largest, if you just translate this plane to this lower plane, you get exact tangential plane. And you get this x. And also you get the function value you get this x, and also you get a gap. This gap is the same as this gap, which is the intersection of this tangent plane to the z-axis. So why am I talking about this? It's because I want to motivate why this thing happens. Okay, so Now, if we plot, so in this, so if we compare this one and this one here, these two equations, if we just take f of x to equal to indicator of this set, do I need to change a variable here? Actually, I need to change my notation here. Instead of using x, I used the z. I just used everything as z. Here we have z, we have z star, and here we have z. But it's z as our variable. So if I use fz to take this node, so when z lies inside this set, okay, my indicator becomes 0. When z1 norm is smaller or equal to 1. When z is outside our this set, I get plus infinity. And because I have a negative sign here, I get negative infinity as my second term. So a maximization over negative infinity will, of course, not be maximal, right? This is a real value. This is not infinity, but this part is negative infinity. So essentially, when fz takes this value, what I'm essentially getting is argmax G transpose Z, Z1 smaller or equal to 1. Okay. And still, I wasn't relating what I've been talking about here to what we actually want to do here. But we'll get there very soon. Okay, so if I just copy from what I already have, is Z star is arg max Z 1 norm smaller or equal to 1 G transpose Z, right? And my intersection with the z-axis. So here, this length. No, actually this position. So it's negative sign here. F star is maximum. This is in terms of G. So now I want to relate. I want you to relate this G to what we are talking about here, the X. So we want to think about. Well, let me just draw the picture here first. Okay. This Z1, Z2, 0 plus infinity. And so, what am I doing here? So, this G is the tangent vector, right? The subgradient vector. I said the subgradient for no, this G is just any vector of the gradient of any plane. And if we relate this G to the subgradient of this function, which takes value 0 here and plus infinity here, we can see the subgradient here at this particular point relates to any vector along this direction, right? So, right, that's example 3. So I want to draw one element from here is that for every coordinate, for every variable, I get a subgradient vector. And now I want to do the reverse. I want to, from this subgradient vector, get this variable. What we've been doing here. So from this subgradient vector, which, for example, I'll take G to be 1, 1. What can get its x? I can get anything on this line. So another example, for another example, maybe if my G is 1, 0, I can get something here, only this part, Z. Okay. So now, not only XX, not only 1, 1, but for any value XX, X1, X. Suppose now this vector G, I also want you to think about this subgradient vector as X. Because we are having this backward in notation, but we just need to think about the gradient as X. Okay, the variable is Z, the gradient is X. Okay, so what we know here is, for example, when x1 equals to x2 greater than 0, we get, remember x is G. We get Z star to be anything on that line segment, right? And for example, x1, a generalization of 1, 0 would be x2 lying between x1 and negative x1, and x1 is greater than 0, for example. Then we get Z star to be 1, 0. Okay. Why are we doing this? This is because I just wanted you to have an intuitive understanding that the subgradient of the indicator function of L1 norm is the infinity norm. Is that true? Anyways, let's look at this part. I haven't shown that the infinity norm is actually the maximum of this function. This is still mysterious f star. And what f star is, suppose your G becomes larger. Okay, G becomes larger. That means, so I have this. This time not a cone, not a pyramid, but I have just a flat board. This is 0, and everyone else is plus infinity, right? If my G, the scale of G becomes larger, that means my plane becomes steeper, and my intersection with the z-axis becomes larger, more negative. And this distance should be actually negative f0 fz. So can you think about how this works? If I have a steeper plane, right, that means my value of g it becomes larger. Then my intersection becomes smaller larger in magnitude. And if my g1 equals g2, then my magnitude actually is this f star g actually is proportional to the scale of g vector. And if my g1 is larger than g2, like what I described here, then here I also, then my f star g is only proportional to the largest vector of g, the largest coordinate of g. So suppose my my gradient of this plane is like this. Compare this with if my gradient of plane looks like this one. So here, if you go from, if you walk this direction, walk unit length, you go up this much. If you walk this distance for this for the same unit length, you go up this much. But if you consider, or should I show you through math? So mathematically, it's pretty straightforward, right? This plane that that passes this point is G transpose. Suppose I call this point Z naught, then G transpose Z naught minus Z, right? And when Z is 0, the intersection, which I call F star G, is 0 minus Z naught, actually negative F star G, is this value. And this is negative G transpose Z naught. But if you look at Z naught, it's only this direction. So only this direction matters. If you go to the other direction, as long as it doesn't go over to here, the other coordinate doesn't matter in the intersection. Okay, everyone agrees? But what happens if your other coordinates go past this line? Then your intersection is not at this point. If your gradient looks like this, then your intersection is moved to here. Remember, every gradient corresponds to only one point or a set of points, but it's unique. So have I done an okay job to convince you that F star G is the infinity norm of G? Yeah? I see 2 nods, but 1 nod comes from the TA, so that doesn't count. So anyways, this is what we can think about this problem. I guess I might have gone too far, but in our case, this is the infinity norm of G, and the scale, the intersection is the infinity norm of G, and the arc max is the point of intersection. The arc max is the tangential point, and the max is the intersection. This is the z-axis.
So I don't know. So what are the
Yeah.
And are you trying to show that the infinity norm is the max of G transpose Z with C1 less than equal to 1? Or are you trying to show something else?
I was just trying to motivate myself why when you have infinity norm like this, you have the subgradient of the infinity norm looks like this one. So to visualize both things, to visualize why the infinity norm takes this form and the subgradient of the infinity norms takes the argmax instead of the max. But still, I didn't explain. Well, perhaps I did intuitively explain why the infinity norm is exactly this form, right? If you follow my argument of the intersection with the perpendicular axis.
So, I mean, the reason why the second equality holds is more direct, right?
The reason that why the second equality holds is more direct. Yes, that's correct.
The infinity norm is max of G transpose Z where Z1 is less than equal to 1.
Yeah. Yes. So from your slides, basically, one example of the convex hull is. So if you haven't understand all the above, that's okay. Let's just start from here. So suppose, okay, let's just start from here. This is the catch. Suppose, I shouldn't say suppose, I should say, this is what we've learned in class, right? Suppose I have this one, which is true if you follow out what I've argued before, but suppose you don't know what I've done, you don't trust me, okay, but you trust drawing, okay, this is true. Then,
No, what I meant is there's a very simple way to see that this is true.
We can just draw it out like in the 2D.
I mean, to see that this formula is true, you can just like from absolute basic first principles see that that is true. So, if for a given G,
okay, for a given G.
like minus 3, 5, something
Mhm.
like this, minus 3, 5, you want to find what maximizes it in the L1 ball.
Yeah. That's what I did. I found for a given G, I found what maximizes in the L1 ball here.
Not geometrically, like numerically.
Oh.
It's going to be the direction in which you have the largest value.
Yeah.
Right? So it's going to be just, I mean, if I want to take minus 3, 5, I want to maximize the dot product with that. I'd rather put all my weight on 5. I'd rather take a dot product with 0, 1.
That's, yeah.
And if it was, minus 2, 1, then I'd rather put all my weight on minus 2. So I'd rather put 1, 0.
Yeah. But then you find this corresponding point, and then you take this cross dot product. You find the intersection with the z-axis, the third axis, and then which is this value. Okay, so this is known, and in class you show from the very important property of subgradient, this is a maximization over a set of points. So basically, what the subgradient is argmax of Z and I should argue that I should put a bracket here, so this becomes a set, because there could be multiple Z's that satisfy this part. And these are convex. These form a convex set because you can see for every given gradient, the z is on this line segment or at this particular point or on this segment. It's a convex set. And this is the catch. This is what I intended to reveal from the class, and I was just giving a graphical interpretation, geometrical interpretation of this part of why this is true. So, okay. So I don't know. I think we should move on to steepest descent, which is the last part of my recitation. Okay. So now I have a, quadratic optimization y minus ax squared, whose level map, it looks like this. This is f of x takes this form, okay? And this is f equals to 1, 2, 3. Right? And if I can compute the gradient of f at x, then this should be my best direction at the very small scale. But somehow we're claiming that this is not our best direction. So it's not because this is like yield conditioned. It's because of something else. So how should I put this? This is our best direction when we are able to search our direction with a fixed unit length x. So basically, we search on this circle of the function values, and we pick the one that decreases the most. So what will happen if this is not a circle? So steepest descent is kind of a generalized gradient descent in that you don't want to search this circle for your descent direction. Instead, you want to search something like an ellipsoid, for example. Why do you want to search for an ellipsoid? Maybe this somehow corrects your skewness of the function. Maybe searching this ellipsoid, you reach a direction that actually works better. Because you're seeing that the effort to go from here to here is the same as the effort to go from here to here. So, but with the same effort, your function decreases more. Or maybe you want to search on a L1 norm, on a fixed L1 norm, then this induces sparsity. So at a particular point, okay, so I have to clarify here. We're talking about continuous functions. We're not. We're leaving from the non-continuous case. We're talking about continuous functions, continuous f, and what might not be continuous is the We're jumping from the differentiable f to a non-differentiable f, okay? And what might be non-differentiable is this norm here. And that's why we still need something about subgradient. So the tangent plane, because we have a differentiable f, the tangent plane basically says you start from x, and this is the gradient times delta x. This describes the tangent plane. Everybody agrees? Okay, so following what I said, I want to find the best direction, find the best arc mean of f bar. F bar is the tangent plane. It's not f. It's the plane that's the local approximation, first order approximation of f. I want to search on this tangent plane when some norm is smaller or equal to 1. For example, p norm. And this is the same as the negative negative of arc max, right? Because everything is symmetric. Here, delta x and delta x is symmetric. Here, the norm is symmetric, like plus or minus. So this arc max of this value, which is the fixed form f of x. Here, I'm evaluating at a fixed x. So this part is fixed. This is a dot product. So basically, we came back to here. And the solution is pretty straightforward. The solution should be negative f q norm, where q is a conjugate norm to p norm. And negative sign applies to both these two places. Okay, any problem? Any questions here? So this is our descent direction, steepest descent direction with respect to the p norm. So again, we're not searching the unit circle, but we're searching some unit norm for our best direction. And I've done a lot successfully or unsuccessfully, but anyways, I've reached this point that you can just see from here that the arc max is the subdifferential. Subgradient, sorry. Okay, so let's see some examples. So, so let me just formalize this things we're doing here. So step 1, we find subgradient of subgradient of the gradient of f at x evaluated at the with the due norm, and this why we find this direction, because it minimizes the negative direction minimizes the descent on the tangent space. Okay, and then step 2. This is a unit vector. Why is this unit vector? Because it's arc max of this constraint. Of course, it is unit vector. And because this is a unit vector, we want to put some we want to scale it according to the gradient. Here, we're scaling it by the due norm of the gradient. And we take the negative as our steep descent direction. And then step 3, you can do a fixed step size gradient descent. You can do a backtracking gradient descent or anything, but at this direction. The direction is no longer the subgradient of f, the gradient of f at x. So anything. Let's see 2 examples. one example comes from the book from Stephen Boyd, Convex Optimization. And here, this P norm is, they're using, this is a semi-definite matrix. And if you expand, this is square of x transpose px, where P is a semi-definite matrix, positive semi-definite. And this has a due norm, which is xq is P negative a half x, a second norm. So this corresponds to the case where I said I want to search on this ellipsoid instead of the circle. And you should trust me that this norm and this norm are conjugate norms, which means basically if I replace this 1 with the first norm and this infinity with the other norm, everything I talked about above still works here. So then my descent direction is the scale of the Q. So let's work this step by step. Okay, step 1. Step 1. This Q norm subdifferential. Because this Q norm here is basically a weighted 2 norm, so it's differentiable, and so this becomes the differential of, should I write it like this? And this is gradient of f. This is gradient of this Q norm. And if I take the gradient of this Q norm, which basically becomes x transpose P inverse x, you can see that the gradient should be 2 times P inverse x. And if I normalize it, it becomes P inverse gradient of f P. This is the unit vector. You can easily verify this. And then I scale it by the Q norm, which is basically this part. So I get steepest descent direction becoming only the term in the denominator, negative P inverse gradient of f. And another interesting example is when this P norm is actually 1 norm. And in this case, sure.
That the subgradient of the Q norm is 1. In step 2.
Step 2.
The one you formalize over there.
Here.
Yeah, that line. Subgradient of the Q norm.
Yeah.
Just that line. Equal to what?
Negative steepest descent direction. So basically, you take steepest descent direction to be negative, the scale times this direction. And for the 1 norm, if xp equals to x1 norm, which is the all often talked about, then the due norm becomes this infinity norm, and the steepest descent direction is basically infinity norm times subdifferential of this infinity norm, right? And so the subdifferential of the subgradient of the infinity norm is basically the convex union of, I just erased it, did I? No. Oh, I probably did already erased it, but yeah, it should be here. But anyways, it's sine of times EI, where these indices, these coordinates reaches the maximum. Okay, and the sine times this value when this part is actually reaches the maximum, I get back what I should. I get back the scale. This is what I get as a steepest descent direction. So again, I want to visualize this part. If I have a very ill-conditioned ellipsoid, for example, like this, okay, and I take this one to be my origin, okay, and my gradient lies here. What this is telling you is you want to find the subgradient of the infinity norm, which is, I believe, if you look at the coordinates of the scale of both coordinates, this is the largest coordinate, so only this coordinate matters. So the subgradient should be here, right? And you will go along this direction. So this is x1, this is x2. Basically, in your first step, you moved x1, but you did nothing to x2. And for several iterations, you won't do anything to x2 until you reach a point where the subgradient actually, the second coordinate actually matters. Then you move towards the x2 direction, but you don't care about x1. And this is very similar to what you've been doing in homework 1, because every time you're just moving one coordinate, basically, almost. And also an important property, property of this method is that it implies sparsity. So if you just move 2 steps, you still get a sparse solution. And in the slides, in the Ryan's slides, he was comparing this with quadratic term plus L1 penalty, and he says if you just if your steps, the number of steps is very small, that corresponds to a high penalty for L1 for L1 penalty. If you your step size if you go through many steps, then that corresponds to this lambda being very small. And there's a correspondence between this method and the basis pursuit and this optimization goal. And this is also known as forward stage-wise regression, because it only goes at one direction at a time, one coordinate at a time. That's all I want to talk about. Thank you for coming.
You have not online, right? Not to be put online, right? It's not being put online.
Yeah, I will.
Hey, I have a question on the homework.
Can I just turn off this? First?